Hello everyone. Today we will discuss about Introduction to Digital Signal Processing followed by Frequency Domain Sampling, which is Module 1 in Digital Signal Processing for 5th semester Electronics and Communication Engineering. In this course DSP, Module 1 teaches you about frequency domain sampling. How do you convert continuous spectra to discrete spectra, reconstruction of discrete time signals, which gives rise to discrete Fourier transform, properties of discrete Fourier transform, problems on them, spectral analysis, followed by efficient computation of DFT using radix 2 algorithms. This completes two modules, followed by filters. You have two types of filters in your syllabus, FIR filters and IIR filters, which is your module 3 and 4, where we learn about design of Butterworth filters, how to convert analog Butterworth filter to digital Butterworth filter using transformation techniques, implementation of them using direct form structures, parallel structure, cascade structures, followed by design and implementation of FIR filters. Next, we will try to implement this on a DSP processors. That is, we learn some of the DSP architectures in our module 5. At the end of this course, the students will have a knowledge of output of LTI system using time domain and transform domain techniques, how do they implement them, different properties of DFT, computing DFT of real and complex sequences, sketching magnitude and phase plot, computing complexity of DFT, that is number of complex multiplication, real multiplications, complex additions. How do we reduce number of complex multiplications using FFT algorithm, that is exploiting properties of Twiddle factor. Finally, design and implementation of FIR filters and IIR filters, and also some basic knowledge of DSP processor architectures. Before starting this subject, let us learn a basic definition of a signal. A signal is a function of one or more variables which conveys information about a physical phenomenon. Some of the examples for signals are our speech signal, image, text what we write, ECG, EEG, EMG and so on. Whereas a system is an entity which takes one or more input signals, manipulates them and gives a new signal for us. Some of the analog systems are clipper, clamper, amplifier. Some of the digital systems are encoder, mux, decoder, further modulator, transmitter, receiver. Many systems are there. As we discussed about signals and systems, the systems can be analog systems or digital systems. Any operation that you do on a signal is called as signal processing. Means signal processing can be done in analog domain or digital domain. If the signal input is analog and output is also analog, such systems are said to be analog signal processors. The clipper, clamper, amplifier that you implemented in your lab are the examples of analog signal processors. Modulator, amplitude modulator, frequency modulator, phase modulator are examples of analog signal processors. Coming to digital signal processing, you have an analog input, whereas you convert that into digital using A to D converters. Now the output of that is digital signal, which will be given to digital signal processors. means processing is done in digital domain. The output of this processor will be digital, which will be converted back to analog using D to A converters, giving an output as analog. Here also input is analog and output is analog, but processing is done in digital domain. Therefore, we call such systems as digital signal processors. Then why do you go for digital signal processing when already we have analog signal process? Means there are n number of advantages. First advantage is digital signal processors are programmable. You can reconfigure our DSPs. The accuracy of the results are very good, easy to store, easy to process. Very sophisticated signal processing algorithms are available in DSP. Luckily, DSPs are cheap compared to analog counterpart. They consume less power and we can use this DSP for many applications. Let us see some of the applications of DSP. As I told you, DSP applications are vast. So some of the applications are edge detection in images, filtering of our data, text, music synthesis, radar applications, satellite applications. We have a digital cameras, we have echo cancellations. You can compress the data in digital domain. You can encrypt the data. You can use it for security purposes. And very important application is medical applications, like you can process your CT scans, MRIs, ECG, EEG, speech. Let us see small example of this DSP. As I told you, let us imagine our input is speech. Speech is analog in nature. Any unwanted signal distortions that we have will be removed using analog filters. This analog filter can work as a band limiting filter also in order to satisfy our sampling theorem to allow finite frequency components. Once our analog input is filtered, we'll convert them to digital using A to D converter. While converting, it's very important that sampling theorem condition must be satisfied. The output of this ADC is discrete time signal X of n. I'll pass it through DSP algorithms or DSP processors. This processor will work as the logic you have implemented, maybe a FIR filter, maybe computing DFT, FFT, wavelet transform. Depending on your requirement, you would have loaded some algorithm to this particular DSP, which gives the results. The results can be displayed either in time domain or in frequency domain. To illustrate this example, I have taken one sinusoidal signal of frequency component 1 kHz. When I pass it through DSP, the Fourier transform of AC cos 2 pi fct, you know that it is AC by 2 into delta f minus fc plus delta f plus fc, that is f is equal to 1 kHz, you have a delta function. So this is your frequency domain representation of signal. Since I have taken only one frequency component, it is called a single tone. In the second example, I have taken two frequency components. So it's a multi-tone. When I apply Fourier transform for this particular signal and see the spectrum, you will have two delta functions, one at 1 kHz, the other one at 3 kHz. So you can observe that computing frequency of this signal, that multi-tone signal, is very difficult. Whereas once you apply Fourier transform and display the frequency content of that particular signal, easily you can make out what are the frequency component present in that particular signal. Now coming to exact syllabus, the first topic is frequency domain sampling and reconstruction of discrete time signals. For this, you must have a basic knowledge of Fourier series and Fourier transform. In signals, you have learned continuous time Fourier series and Fourier transform. Similarly, discrete time Fourier series and discrete time Fourier transform. When we apply discrete time Fourier transform for a aperiodic finite energy discrete time signal x of n. So we are trying to apply discrete time Fourier transform for a aperiodic finite energy signal. The formula is x of omega is summation n varying from minus infinity to plus infinity x of n into e power minus j omega n. X of n is time domain signal, x of omega is frequency domain representation of x of n. When we observe x of omega, the spectra has become periodic with a period of 2 pi, as well as it has become continuous. Try to understand and remember this word. Discrete time Fourier transform of a discrete time signal is continuous and periodic. This continuous and periodic signal cannot be applied to DSP. So we must perform sampling in frequency domain to convert continuous spectra to discrete spectra. So what we'll do is we'll consider one cycle of this spectra. Within this one cycle, I'll collect n number of samples. Each sample separated by a distance of delta omega defined by 2 pi by n. To fetch each sample, I'll multiply by an integer k. Means wherever omega is there, if we replace it by 2 pi by n into k, such process is called as sampling in frequency domain. Therefore, our equation 1, which is our DT-FT formula, now converts to x of 2 pi by n into k is equal to summation n varying from minus infinity to plus infinity x of n into e power minus j omega n was there in equation 1. Now I have replaced omega by 2 pi by n into k, where k is an integer varying from 0 to n minus 1. See the beauty of this particular DT-FT concept. The spectra is periodic. After every 2 pi, same signal is repeating. So the summation is varying from minus infinity to plus infinity. You can divide this summation into different summations, each having only n samples. So we rewrite this formula as different summations. The first summation is from 0 to n minus 1. Next summation is from n to 2n minus 1. Further from 2n to 3n minus 1. Similarly, minus n to minus 1. So we have infinite number of summations from minus infinity to plus infinity, each summation handling only n samples. So writing this complete equation is difficult. We try to combine this equations as sum of summations. So we'll introduce a notation L varying from minus infinity to plus infinity, and one more summation from ln to ln plus n minus 1. Observe, L is also an integer. If I put L is equal to 0, the inner summation becomes from 0 to n minus 1. This is what we have written. If you put n is equal to 1, it becomes n to 2n minus 1. That is the second. If you put L is equal to minus 1, this summation you get. So by substituting different values of n, you get back all your summations from minus infinity to plus infinity. Now I want to make this lower limit as 0. So I'll make a substitution in inner summation, that is n to n minus ln. Afterwards, using linearity property, I can interchange the order of summation also. So once I do this, our outer summation now will be 0 to n minus 1, inner summation minus infinity to plus infinity, This x of n becomes x of n minus ln e power minus j 2 pi by n into k into n minus ln. This term looks like the last term e power a minus b. This e power a minus b can be written as e power a into e power b. So I can split this e power a minus b as e power a into e power b. Now observe the second term. This is e power j 2 pi by n into k into ln. I can cancel these two n. So it becomes e power j 2 pi. So e power j 2 pi or multiples of 2 pi will be equal to cos 2 pi plus r minus j sin 2 pi, which is always equal to 1. So I can leave that summation. Left out term is only so much. Observe the summation within this flower bracket. This looks like periodic representation of your x of n. So we'll denote this term by xp of n, where xp of n is the periodic representation of x of n with the period n. Any periodic signal can be represented using Fourier series as xp of n is equal to summation k varying from 0 to n minus 1 ck into e power j 2 pi by n into kn, and with Fourier coefficients ck is equal to 1 by n summation 0 to n minus 1 xp of n into e power minus j 2 pi by n into kn. When we observe this formula, the Fourier coefficient formula, with our sample spectra, almost all both looks like same. Observe your equation 3 with your equation 3 with equation 6. We can conclude that Fourier coefficient Ck is equal to 1 by n into this complete summation looks like x of 2 pi by n into k. And we will substitute this equation in 5, becomes xp of n is equal to 1 by n into summation k is equal to 0 to n minus 1 x of 2 pi by n into k into e power j 2 pi by n into kn. Almost all we are reaching to reconstruction. This formula becomes a reconstruction formula for us in further. So I have given you an idea of reconstructing our signal xp of n from the knowledge of x of 2 pi by n into k. So all sample spectra can't be reconstructed. There must be one condition. So let us assume that I have a signal x of n with the length equal to L. Observe, I have taken some values like 5, 4, 3, 2, 1 followed by zeros. I will apply DTFT for this. My spectra will be continuous, periodic. I will sample that. So when I am doing this sampling, I want to choose my n number of samples in such a way that it should be greater than L. If I choose n greater than or equal to L, I will not get any aliasing. So reconstruction is possible. Whereas if I choose n less than L, reconstruction is not possible. Aliasing occurs. So always you must choose the value of n in such a way that it should be always greater than or equal to number of samples given. So very important condition is, for the proper reconstruction of our signal, the value of n should be always greater than or equal to L. Otherwise, we can't reconstruct x of n from the knowledge of xp of n. If you choose n value less than L, we get a aliasing. With this, we'll start discrete Fourier transform. Whatever derivation we did is an example of discrete Fourier transform only. We'll put it in a proper form. Let us take x of n, which is a finite duration length sequence of L, which is always less than or equal to n I have chosen. So, its periodic representation of the signal is xp of n contains the value of x of n from 0 to L minus 1. Afterwards, it will have some zeros. If this condition is satisfied, the Fourier transform, which is discrete time Fourier transform of that particular signal x of n, is defined as x of omega is equal to summation n varying from 0 to n minus 1 x of n into e power minus j omega n. In my previous derivation, I told you that wherever omega is there, you replace it by 2 pi by n into k, which is said to be sampling in frequency domain. So, I have replaced omega by 2 pi by n into k. And this complete formula can be approximated as x of k is equal to summation n varying from 0 to n minus 1 x of n into e power minus j 2 pi by n into kn. And this formula is called as discrete Fourier transform formula. X of k, k represents discrete frequency index. Discrete frequency index. And what we will do now is we represent this e power minus j 2 pi by n by using twiddle factor or phase factor defined by omega n. It should be capital N. Omega capital N is equal to e power minus j 2 pi by n into k. Therefore, our DFT formula becomes x of k is equal to summation 0 to n minus 1 x of n into omega n power kn. We can get back x of n from the knowledge of x of k using a formula called as inverse discrete Fourier transform formula defined by x of n is equal to 1 by n summation k varying from 0 to n minus 1 x of k into e power plus j 2 pi by n into kn, where n is a variable from 0 to n minus 1. Again, this formula can be represented using twiddle factor, that becomes omega n power minus kn. Complete module 1 and 2, we will be discussing only these two formulas, that is DFT and one more is IDFT formula. Observe these two formulas, DFT and IDFT. In both the formulas includes sum of products. Try to observe this. It's a product between x of n and omega n power kn, and all such products must be added. So it is a sum of product problem. Similarly, IDFT is also a sum of product, then extra a scaling factor. In literature, we always represent this as a transformable pair, that is x of n with a n point DFT becomes x of k, or x of k with n point IDFT will become x of n. Therefore, these two are said to be transformable pairs. To compute n point DFT of a sequence, from this equation, the summation is varying from 0 to n minus 1. So, you require n number of products, n products. So, to add this n products, you require n minus 1 adders. But this formula is repeated for k varying from 0 to n minus 1, means n times. Try to understand. In this summation, you have n products and n minus 1 additions, and this formula is repeated for n times. So totally it requires n into n square complex multiplication, so n into n minus 1 complex additions, because Total factor is a complex number where input can be a complex or real. So totally, to compute n-point DFT of a sequence using formula method, we call them as direct computation of n-point DFT requires n square complex multiplications and n into n minus 1 complex addition. As I was saying, these two formulas looks like sum of products. Why can't we handle this as a matrix multiplication? Handling this DFT formula as matrix multiplication is called as DFT as linear transformation. So, first let us define a input vector equivalent to x of n, xn. It's a matrix of 1 uh, n rows and 1 column. So only I have written xn defined like this. This is a column vector, column matrix which consists of only input sequences from x of 0, 1, 2 up to x of n minus 1. Once you perform DFT on the sequence, you get x of k denoted by capital X and n, xn. It's a vector, it's a matrix again of order n cross 1, capital X of 0, 1, 2, n minus 1. Now this input vector will be multiplied with a n cross n matrix called as Tudel factor matrix. This is a Tudel factor matrix where the first row contains omega n power zeros. The next row contains 0, 1, 2, 3 and so on. Next row contains 0, 2, 4, 6. Next row contains 0, 3, 6, 9. And the final row contains 0, n minus 1, 2 times n minus 1 and so on. However, this Tudel factor matrix is a n cross n matrix. We will multiply this n cross n matrix with the input vector to get x of k. So a simple matrix multiplication between Tudel factor matrix and input matrix will give rise to x of k. Similarly, we can try out for IDFT also. From the equation, to get back my x of n, I can multiply omega n power minus 1, that is the inverse, into xn. So when you observe our IDFT formula 100%, it also looks like a matrix multiplication, but not between xn and Tudel factor. It's a Tudel factor complex conjugate, that is omega n star multiplied with x of k matrix scaled with 1 by n will get back xn, that is x of n. So easily we can handle these two formulas as matrix multiplications because our computers, our DSPs will easily implement DSP formulas in a matrix form. So we can multiply these two to compute DFT and IDFT of a sequence. So from this complete session, we learned that what is frequency domain sampling, how do you convert continuous spectra to discrete spectra, how can we recover discrete spectra from the knowledge of continuous spectra, how to avoid aliasing effect, formulas for discrete Fourier transform and discrete Fourier transform. Thank you.